Welcome back to the lectures on chemistry. This is the last lecture in the course, the short introductory course on molecular spectroscopy that I started giving about 2 months ago. And in this particular lecture I want to summarize all the important results so that it would help you in keeping this up in your studies and also towards the test that you wanted to write in the coming weekend and also the weekend afterwards, one of the 2 weekends. So let me first of all tell you that I have enjoyed obviously giving this course in public domain and have had quite a lot of interactions with a few students here and there. But unlike a massive open online course, the number of interactions I have had is not that many. Hopefully these things will improve as you read more and more. Let us get to the topic, namely the review of basic concepts, which I hope you would take it as the lesson forward and as a take home lesson, if any, for the next course, any advanced activity in molecular spectroscopy. This is the final lecture for this course. There may be supplementary readings, but they are not part and parcel of the final examination. Okay, we started with electromagnetic radiation as the first object and its interaction with matter was defined as the basic area of molecular spectroscopy. And if you recall, we used the Einstein relation E is equal to h nu, where this is the Planck's constant and this is the frequency of the radiation that interacts with the substance and the energy of each photon. Is given by its frequency with the Planck's constant here. This was also written as E is equal to h c by lambda, where lambda is the wavelength of the radiation and c is the speed of light in vacuum. We did not do calculations for the wavelength or the speed of light in other media, but we assumed the vacuum. And the last thing was also to write this as hc into 1 by lambda or equal to hc nu bar. These are the 3 fundamental relations that we needed to use. The frequency, energy is proportional to that. The lambda, the wavelength, energy is inversely proportional to that, and the wave number, energy is directly proportional to that. With these 3 things as the 3 properties defining the radiation, then we decided to look at the electromagnetic spectrum and came up with the radiation all the way from radio waves to cosmic radiation. Okay. That is the whole range of electromagnetic radiation frequencies of the order of about 15 orders of magnitude, 15 to 20 orders of magnitude, and therefore we saw that the radio waves were important in interacting with the magnetic property of the matter, and that led to what is called as the magnetic resonance, which we did not look into this course. And then microwaves, which also interacts with the magnetic properties of the electron to give you what is called the electron paramagnetic resonance. So those 2 branches, the nuclear magnetic resonance, which is the result of the interaction of the radio waves of electromagnetic radiation with the nuclei which are placed in a static magnetic field, to that of the electron in microwave. Both of these were called magnetic phenomena, and then we studied only the optical phenomena, namely the interaction of electric component of the radiation with matter, and that we studied using 2 branches of spectroscopy, microwave and infrared. Briefly, I lectured a bit about the electronic spectroscopy in one of the lecture notes. I believe it's in the lecture 1 of the PDF towards the end of it, where I also talk about the Born-Oppenheimer approximation and how the electronic transitions are called the Franck-Condon transitions and so on. Very, very briefly I introduced that, but in the lectures I have not given that. Okay. We spent a lot of time looking at the microwave radiation, infrared radiation, and also the properties which were responsible for the radiation to absorb in the microwave range and also to absorb in the infrared range. This was the second step. But even before that, when we looked at the electromagnetic radiation, we looked at a couple of important phenomena called the absorption, emission, and stimulated emission. If you recall, we had these pictures about the molecular energy levels, the lower energy level and the upper energy level, and the radiation falling on the molecules in their lower energy level, causing them to be excited. If the radiation has the frequency h nu, which corresponds to the gap between these two energy levels, there is a possibility that this radiation will be absorbed. And since the radiation will also fall on the excited molecules, it is possible that the radiation will stimulate the emission of molecules from the excited state to the lower energy or the ground state. So the absorption and the stimulated emission, both of which were caused by the radiation, were also approximately proportional to the number of molecules in the respective state. And for radiation, we use the radiation density rho nu. Okay. Therefore, the absorption process is proportional to both the radiation density and the number of molecules which are in this energy state, which allows the molecule to get excited. And the stimulated emission is, the rate of stimulated emission is proportional to the number of molecules in the excited state and also to the radiation density. But independently, there was this process where molecules which are in the excited state spontaneously decaying to the lower energy state and releasing a quantum of energy. When this happens, this releases 2 quantum of energy and this absorbs 1 quantum of energy. Okay. Absorbs. So this process was also described to you with the corresponding balance equations for the rates for a system in equilibrium with the radiation, a system in thermal equilibrium and also in equilibrium with the radiation at a given temperature. And these rate equations were used along with what was known as the Max Planck distribution law for the radiation density as a function of the frequencies of light emitted by idealized bodies such as the black bodies. And this led to some relation between the absorption coefficient or the emission coefficients, the stimulated emission coefficients, both of which are equivalent to the spontaneous emission coefficient. This was a process which was important for us to understand as a semi-classical way of understanding why molecules absorb energy, and therefore all the things that happen in the molecules happen as they are. Okay. Then we moved on to study the molecular domain with specific properties such as the microwave radiation absorbing, being absorbed by the molecule, causing changes in the rotational energy level. Okay. We looked at what was known as the rigid rotor model. For the rigid rotor model, we used the rigid body kinetic energy, namely E kinetic energy is the square of the angular momentum divided by twice the moment of inertia, and in the case of quantum mechanical systems, the angular momentum being an operator, the Hamiltonian for a rotating system in which the equilibrium configuration did not change, that is why it is called rigid body. The molecule remains intact, there is no vibrational motion or there is no displacement about equilibrium. It is an approximation, because molecules do vibrate even at 0 Kelvin, but a rigid molecular approximation means that the molecules, the atoms do not move around their equilibrium, they stay rigid, and therefore the moment of inertia does not change. For such a system, the Hamiltonian was written as J square by 2I, and for a simple diatomic molecule with a reduced mass mu given by m1, m2 by m1 plus m2, where these are the masses of the individual atoms in the diatomic molecule, the moment of inertia I was written as mu dot r, mu times r square, where r is the interatomic distance or the bond distance at equilibrium. This was used to solve, of course I gave you the solutions, and quantum mechanics tells us how to solve this problem by writing the Schrodinger equation H psi is equal to E psi, and this gives you J squared by 2I acting on psi, J being the operator, giving you E psi, and this E turns out to be H bar square J into J plus 1, a quantum number J, where J is 0, 1, 2, 3, etc. Okay. This was the solution that we had used. Therefore, what you have is H bar square by 2I. Okay. Yeah. J square by 2I. So, the solution is J square acting on psi gives you H bar square J into J plus 1. Therefore, this by 2I gives you that. So, this was called the energy Ej, and the wave function corresponding to that was called psi j and Ej. Later we would find out that the psi j itself is 2j plus 1 fold degenerate, but I will get to that in a few minutes. This is Ej, and Ej is given by H bar square, which is H square by 4 pi square into 2I times j into j plus 1 times psi j, and this whole quantity, which is called the Ej, was written as a wave number times the appropriate constants, namely Ej was written as Hc times Hc times b times j into j plus 1. Okay. This b, by definition, because of Hc into b being h square by 8 pi square I, okay, b turns out to be h by 8 pi square Ic, and the introduction of b was to tell you that spectroscopists use this, namely wave number unit, for measurement of spectroscopic, the measurement of distances between the lines, and also to identify spectroscopic lines. So, B is, this whole thing is energy, Hcb is energy, and when you divide it by Hcb becomes what is called the rotation constant. And this rotation constant B is obviously related to the molecular interatomic distance 8 pi square times mu r square because of the I times C. And given the molecule, you know what the mu is. Given the experimental data for the splitting between different lines, you know what the B is, and therefore C and H are constants, and you can calculate the interatomic distance R. If the atomic species are substituted by isotopic, different isotopes, isotopic species, then isotopic substitution leads to a change in the value of B because mu also changes. So, these are things which I requested you to do some manipulations in terms of simple tutorial problems and also in the regular lecture. This is for the diatomic molecule, but then all of this is possible only because if the diatomic molecule has a dipole moment, which is also written in terms of the mu, symbol mu, but mu with an arrow, meaning that the dipole moment having a direction. So suppose there is a delta plus here and a delta minus here due to electronegativity difference, then the mu is given by this direction times, that is whatever is the distance, the bond distance between the two atoms, times the charge difference, namely the delta plus or delta minus, the delta plus giving you the dipole moment. It is the dipole moment which undergoes oscillations. In this case, of course, it undergoes rotations as the molecule rotates about all the three of its axes. But if you look at this axis, the moment of inertia about this axis is 0 because the masses are concentrated on the line itself, on the axis itself. Therefore, there is no perpendicular distance r from the bond axis. So, this I is 0, and this also does not lead to any dipole moment change because the molecule is rotating about its own axis. There is no change, and this is not a rotational degree of freedom. In fact, this does not change anything. Therefore, a diatomic molecule has only two rotational degrees of freedom, namely about an axis passing through the center of mass of the molecule and perpendicular to the bond, and also another axis perpendicular to the bond again, but also passing through the center of mass. These are the two moments of inertia, and both of these are equal. Therefore, a diatomic molecule is a very special case in which there are moments of inertia about two mutually perpendicular axes. So, if the diatomic molecule is like this, one axis is this, the other axis is this, the third axis, which is perpendicular to both of these and along the bond, does not contribute to rotational motion. So, you have 2 degrees of freedom, and the overall angular momentum that you talk about is the sum of the 2 degrees of freedom about those two axes and with the same moment of inertia. So, this is the microwave spectrum for a rigid diatomic molecule, and molecules needed to have dipole moment because during a rotation the dipole moment will be perhaps pointing like this. After some it will rotate and then like this and then like this. If you draw this, the dipole moment rotates about an axis which is perpendicular to that, or the dipole moment rotates in and out of the plane. The dipole moment comes out and then goes into the plane, and therefore it rotates about the axis. So, those two such rotational motions lead to electric charge acceleration, the motion of the electric charge, the dipole moment. Therefore, they will resonate with the electromagnetic radiation of an appropriate frequency, leading to absorption of energy and leading to microwave transitions. And the microwave transition had a selection rule, namely delta J is equal to plus minus 1, meaning that if the energies Ej are given as Hc B j into j plus 1 and Ej by Hc, if we write that, then Bj into j plus 1 tells you that the energy levels for a diatomic molecule are arranged in this order. J is equal to 0, J is equal to 1, and the gap is 2B, because when J is 1 it is 2B and the difference is 2B, and then it is for 6B for J is equal to 2 and 12B for J is equal to 3, 20B for J is equal to 4, and so on. So, you see that the successive energy levels differ by 2B, 4B, 6B, 8B, and if all of them appear as spectral transitions, there is a transition at 2B, there is a transition at 4B, there is a transition at 6B, it's a transition at 8B, and so on. And so what you see is, if this is the increasing frequency, the gap between any pair of successive lines is also 2B, 2B, 2B. because this is a line at 2b, this is a line at 4b, this is a line at 6b, this is a line at 8b and so on. Therefore, you see the difference between any pair of successive lines in a rigid body microwave gas phase rotation spectrum is given as 2b, and from the fact that b is given by h by 8 pi square mu r square c, right away you can calculate the bond distance. It is possible only if the molecule has a permanent dipole moment. Microwave spectra cannot be obtained for molecules without a permanent dipole moment, and this was used in some of the tutorial problems for you to determine which molecules will have microwave rotation spectrum and which do not, and so on. Okay. So, this was the introduction to microwave spectroscopy, with one last thing, namely the intensity of these lines. Here I have written this as, if you write this as nu b, if 2b is this, the next one 4b is slightly of a higher intensity, 6b is of a higher intensity, until it reaches a point when the intensity is maximum, and then the intensities fall off for successive transitions. And we knew that the reason was due to the fact that the number of molecules in any energy level J prime divided by the number of molecules in any other energy level J double prime is given by the degeneracy of that energy level J prime, which is 2J prime plus 1, divided by the degeneracy of the energy level corresponding to this, which is 2J double prime plus 1, times exponential minus E J prime minus E J double prime over KBT, at any given temperature, and Kb is the Boltzmann constant, and this formula was used to calculate the different intensities and the ratio of the intensities from lower to higher, and we found out that this whole formula fits into an approximate nu J max. If I have to write, the J max is happening at approximately the number 2 kBT by HCB minus 1/2. This was also shown in one of the lectures, meaning that the intensity of absorption for a rotational spectrum has an envelope of this kind, and the maximum is given by the corresponding value of B and is also proportional to the square root of T. This is as far as the microwave spectrum is concerned. Let me continue with the next short summary of the polyatomic molecular microwave spectroscopy in a minute.